So today we are going to start chapter 7. We're going to cover the Pythagorean theorem today. So in a right triangle, so we've already been practicing this, so this will be a nice easy lesson for you. So we only will use the Pythagorean theorem when we have a right triangle. So in a right triangle, the squares of the lengths of the hypotenuse is equal to the sum of the squares of the lengths of the legs. Now, you can switch up the A and the B. However, the C always has to be the hypotenuse. It's always going to be across from the right angle. So that's the only thing that you can't change. The C is always your hypotenuse. These are going to be the legs, the A and the B. And it doesn't matter which one you label as A and which one you label as B. Next. These are actually some common Pythagorean triples. These are all numbers that if you were to plug them into a squared plus b squared equals c squared, they would satisfy and form a right triangle. Remember, the largest number in these triples is always the hypotenuse. It's always your C. Now, you can scale them up, or like, for example, a common triple is this 3, 4, 5. You might see the 3, 4, 5 triangle quite often. I think it appeared quite often in our review. You might see it a lot on PSATs or SATs. Notice to get to this next triple, all they did was take the three numbers and multiply them by 2. So you can scale them up by multiplying them all by the same number. Another common triple is a 5, 12, 13. Notice the 5 is a leg, the 12 is a leg, and the 13 would be the hypotenuse. So for example, on this 3, 4, 5 triangle, if you had a right triangle, remember that the 4 couldn't be here, okay? And then the 3 and the 5. This would not work. This would have to be the 5, and this would have to be the 4. Remember, the hypotenuse, or the largest number, is always across from the right angle. So the largest number is always going to be your C. So this could be A, this could be B. It doesn't matter if the 3 is the A or the B, or vice versa for the 4. But the hypotenuse is always going to be the biggest number, the C. All right, so here are 3 examples of right triangles, and they want us to find the missing side. Now notice none of these are a triple, none of the triples that we just saw. Now, keep in mind that if we have square roots, we're not using a calculator, so we're going to leave things in simplest radical form. Also, just one thing to remind you about is, remember, your figures are never drawn to scale unless they tell you that they're drawn to scale. So you can't look at it and say, oh, this one looks shorter than this. Never go by what the picture looks like. Always just apply your rules. So let's do the first example. Again, the side that's across from the 90-degree angle, this is really my C. This could be my A, and this could be my B. So I could do 5 squared. So I'm doing A squared plus B squared equals C squared. So 5 squared plus 10 squared, and I'll use the letter that's there, Y squared. I need to square the 5. Now I can't add 5 plus 10 first. I need to square the 5, square the 10, now add them, and I don't want the value of y squared. I want what y equals. So in order to find out what y equals, I need to square root both sides. So y is equal to the square root of 125. Now, we need to leave things in simplest radical form, so now I need to break down the square root of 125, so I'm going to do a factor tree. So I could do it over here. So if I take 125 and I figure out what I can multiply to get 125, I could do 25 times 5. I'm going to still break down until I'm in prime numbers. Oh, I can't see that 5 now. So 5, 5, 5. So now I look for pairs. These are all still under square roots. Once I make a pair, 1 comes out, and anything else that doesn't pair up stays underneath. So in simplest radical form, my answer for y is 5 square root 5. So that's what y equals. Pretty good so far? All right, let's try B. Now this one's bringing a lot of algebra back to us. So again, the legs, or the two sides that form the right angle, this could be A, this could be B, and this could be my C. So I'm going to do 5 squared plus y minus 1 squared equals y squared, because this is a squared plus b squared equals c squared. Now, be very careful when you're doing this one. You can't just distribute that square. You got to FOIL this. So this is where all of our algebra skills are coming back. So really, this middle term, the y minus 1 squared, really means y minus 1 times y minus 1. I'm going to FOIL it. Y times y is y squared. Outside gives me 1y. Inside gives me 1y. And last gives me plus 1. I'm going to add the two middle terms. And I get negative 2y. So now let's go ahead. This is what I get when I square that middle thing. So 5 squared is 25. The y minus 1 squared is y squared minus 2y plus 1 equals y squared. I now need to start combining my like terms. So I could add 25 plus 1. And then I get y squared minus 2y equals y squared. I now need to try to get my y squareds together. So I'm going to start combining terms. Notice it cancels from both sides. So 26 minus 2y equals 0. Going to move the 2y to the other side. 26 equals 2y. Divide by 2. And y equals 13. So now I'll come back. So this side is 13 minus 1, which is 12. And this side is 13. If you recall from the previous slide, we did have a triple, and it was the 5, 12, 13. And that's what I just formed. So this one was really algebra intense. We're bringing back a lot of algebra skills in this problem. So just make sure you're very careful. Because a common mistake when students see this, they're going to think that they could just square the y, square the 1, and get this, and that's wrong. So you need to remember that whenever you have a binomial that's raised to a second power, to a third power, you need to use distributive property or FOIL. Let's try the next one. Okay, C's down here. Now this is the square root of 2 that's here. Let's see, square root of 2. So again, this could be A, this could be B, and this is my C. So A squared plus B squared equals C squared. So x squared plus 3 squared equals 3 square root of 2 squared. So let's square each piece. So this becomes x squared plus 9. Now, when I do this, I'm really doing 3 square root of 2 times 3 square root of 2. That's what squared means. Now, when I do this, I'm going to do outside times outside, and I get 9. And then when I multiply the square root of 2 times the square root of 2, that gives me the square root of 4, which is just 2. Remember, whenever you multiply a radical by itself, the radical just disappears. So then this becomes 9 times 2, and I get 18. Gonna subtract the 9. X squared equals 9. I need to square root it. Now, when we do this in Algebra 2, we're actually going to get plus and minus 3, but because we're looking for a side length, I'm going to throw away the negative answer. So the only thing I need to keep here is positive 3, the square root of 9. So x equals 3. This is actually an isosceles triangle. Now, again, what I had said about not drawn to scale, if you first look at this, you're thinking, these don't look like they're the same length. But again, remember, figures are not drawn to scale. So don't go by what it looks like. And we're going to learn about special right triangles. And this is one of the special cases. But for now, all we're doing is applying Pythagorean theorem. So in my next example, it wants me to find the length of a diagonal of a rectangle with a length of 8 and a width of 4. Now, whenever you're given a problem and a picture is not provided, you should draw your own picture. So let me go ahead and draw a picture of a rectangle. Remember, a rectangle has 4 right angles. Now, I know we have not covered quadrilaterals yet, but I'm sure everyone is familiar with what a rectangle looks like, and you should all realize that each corner is 90 degrees. Now, it wants me to find the length of the diagonal, so I'm going to draw a diagonal in here, and then it's telling me it has a length of 8 and a width of 4. Notice when I just drew in that diagonal, I've now created 2 right triangles. Also, another property of a rectangle that you should be familiar with is that opposite sides in a rectangle are congruent. So notice both of these triangles I just formed both have the same leg lengths. So again, the diagonal here is going to be my C. It's my hypotenuse. So again, I'm going to use Pythagorean theorem to find the length of that diagonal, which is the hypotenuse. So I could say this will be A and this will be B. So 4 squared plus 8 squared equals C squared, which is my diagonal. 4 squared is 16. 8 squared is 64. I'm now going to add them. And I get 80. Now, again, we're not using calculators, so we're going to leave our answers in simplest radical form. So again, I need to see if there's any perfect squares hiding in the 80. And the way that I do that is I do a factor tree. So let me go ahead and factor out 80. It doesn't matter what you start with. What do you want to start with? What times what gives me 80?
20 times 4.
20 times 4, okay. Now, I need to keep breaking these down until they're prime. So 4 is 2 times 2. 20, I can either do 2 times 10. I'll do that. 2 times 10 or 4 times 5. It doesn't really matter how you break it down. Now that I've done this, I'm at prime numbers. Now I look for pairs. I have a pair of 2s, and one of them comes out. I have another pair of 2's. One of them comes out. Nothing to pair with the 5. He stays under the radical. Anything that comes out, we need to multiply. And the same thing would happen if there were extra numbers left underneath that didn't pair. You multiply them back. So this will simplify to 4 square root 5. So our diagonal length, equals 4 square root 5, which is what c squared equals, or c equals. Now, again, if I would have done 8 times 10, I'm still going to get the same answer. Some of you might have realized that it was 16 times 5, and then if you realize 16 is a perfect square, you could square root it and then go right to the 5. It doesn't matter how you break down your radicals. Some of you are going to be really quick and you could find the largest perfect square and just square root it. Other of you are going to have to go nice and slowly and do 4 times 20 or 8 times 10. It doesn't matter. You still get the same answer no matter how you break it down. Pair 2's, and then the 5 stays underneath. And you still get the same answer. So again, all answers need to be left in simplest radical form. Let's try the next one. All right, so here, another application problem, and it's telling me that the diagonals of a rhombus have length 16 and 30. It wants me to find the perimeter of the rhombus. Now, I understand that we have not covered quadrilaterals yet, and we're going to learn all the properties of the different quadrilateral shapes. But for this question, does everybody understand what a rhombus looks like? Looks like a diamond, right? Okay, so let me go ahead and draw one. So here is my rhombus. Now, some of the properties that you haven't learned yet is for rhombus, all sides are congruent. Another property of a rhombus is that the diagonals bisect each other. You're also going to learn that the diagonals are perpendicular. So notice I have now just created 4 little right triangles. My diagonals have been bisected, so one of them's 30. So I could say this one's 15, this one's 15, and then the other one would be 8 and 8. So now, once I do one of the right triangles and get this side length, which is the same for all of them, then I can add them all up. So I'm just going to focus on one of the triangles. It's got a leg of 15 and a leg of 8, and I'm looking for the hypotenuse. So I can do my Pythagorean theorem. My a squared plus b squared equals c squared. Yes. I took my lengths of my diagonals and I split them. Because what we're going to learn coming up is that the diagonals of my rhombus are bisected. So if this whole thing is 30, I could split this into 15, or actually let me do it the other way that I showed it. So this one, if this whole thing here is 30, then I can say this one's 15 and this one's 15. And then if this whole thing here is 16, then this side would be 8 and this side would be 8. So again, I know you haven't learned about the properties of a rhombus, but just you're going to learn that the diagonals bisect each other. They form perpendicular lines, which can make us form right triangles. So again, I'm using a squared plus b squared equals c squared. It doesn't matter if the 15 is a and the 8 is b, or vice versa. You can switch them up. So let's try this. So 15 squared, do this in yellow so you can see it. So 15 squared plus 8 squared equals c squared. 15 squared is 225. 8 squared is 64. I'm going to add those and get 289. And then square root this, and I know it's kind of big, but this is actually a perfect square, and the square root of 289 is 17. So you really should memorize the perfect squares up to 20. So you should know 12 times 12, 13 times 13, 14 times 14. If you don't, you're going to have to guess and test because you don't have a calculator. So, use 20, like 20 times 20 is 400. And if you know 12 times 12 is 144, you know it's going to be somewhere in between 12 and 20. And then from there, start guessing and testing and multiplying. So now, it didn't ask me for the side length of the rhombus. It asked me for the perimeter. And again, I know that all sides are equal or congruent in a rhombus. So this one's 17, 17, 17, 17. So I can either add those or just multiply by 4. So the perimeter of my rhombus is 68. It didn't say if these were centimeters, so I could say 68 units. One more example. Bringing back our altitudes and our medians and our perpendicular bisectors. So again, remember, technically, we're starting a new semester and the final exam would only cover second semester. However, anything we've covered since August is fair game on any test or any quiz or even your final exam. So any prior knowledge, especially when we get to the quadrilaterals, you're going to be using those alternate interior angles, corresponding. All of that's coming back. Nothing goes away. So you need to keep all this information fresh because we'll continually use it. So let's try our last example. Now, I actually have 3 different triangles here. I've got the one large triangle, and then I've got 2 smaller ones. Does anybody recognize what type of triangle the whole big triangle is? Isosceles, good. You guys remember your base angles theorem? Where you have 2 sides that are the same, then that means the 2 base angles are the same. So notice these 2 sides tell me that these 2 angles are congruent. Now, I've also got an altitude in here. So this little line here that goes from the vertex to the side over here, forming a right angle, this is the altitude of my triangle. Yes?
So for the base angles theorem, isn't it like the diagonal angle? Not like the angle that's like straight down?
So I'll just put it like this. I'll flip it around. This is the vertex angle. And then when you have 2 sides congruent, then the angles across from those sides.
Okay, I got confused before.
Yeah, because it's upside down. Yes. Okay. So in addition to this 6, this line through the middle being an altitude, it's also a perpendicular bisector, and it's also a median. It's hitting the midpoint. So if this side is 6, then I know that because that is the midpoint where that median is hitting, I know that that side is 3. So now to find the value of x, I'm just going to do Pythagorean theorem because I have a and b. I have 2 legs. So now what I'm going to do is work with one of these triangles. This could be a, this could be b, and this will be my c. So again, a squared plus b squared equals c squared. So 6 squared plus 3 squared equals, I can call that x squared or my c squared. Now, it didn't matter if I labeled the 3 as A or B and then the 6 as A or B. It didn't matter. Those are interchangeable. So I get 36 plus 9, 45. Again, I don't want x squared. I want only x. So x is equal to the square root of 45. Again, I need to see if I can simplify that 45. So let me do my factor tree here. 9 times 5. Now, if you realize right here at this point that 9 is a perfect square, you could square root it. However, if you didn't realize that, keep breaking it down till it's prime. At this point, if you're doing this method, you got a pair of 3's. So one of the 3's comes out, and then the 5 that didn't have a pair stays underneath. So this final answer here, the value of x is 3 square root 5. So when you're taking your testing quizzes, make sure that when you're doing this Pythagorean theorem, show the work. Show me what you got before you tried to break it down, just in case you're looking for partial credit. Let's say you got to 45 and at this point you messed up when you were trying to break it down. If you've shown the work, you know, you can get some partial credit there. So again, we're not using a calculator. We're leaving our answers in simplest radical form. So you have the homework for this. It's due tomorrow. When you come in tomorrow, you should be working on the 7-1 warm-up. Now keep in mind, as you've seen in the past, a lot of times the warm-ups reflect the test and the quizzes. So don't come in and figure out, oh, she's not going to collect it, I'm not going to do it. It's important that you're doing these warm-ups. They help reinforce the lesson. So you have homework, it's 7-1. Tomorrow we will do the converse of the Pythagorean theorem, which will be 7-2.